and we'll try to load it up appropriately such that you guys have access to it. But don't bank on it. Don't tell me that you promised us that your video lecture and it's not there. So you know what? We don't have a clue. Well, I can say we don't have a clue, but we don't really have big experience in doing this. The RAND folder, that camcorder, and all of this stuff from the library, because now this is normal material, and we are trying it out to see if it works out. And if it does, good for you, because you'll be able to use it. All right, kiddos, do not come to this class if you are more than 10 minutes late. You are not allowed in. Today is okay, but don't try from tomorrow, please. Okay, it's not going to go over well, because I know all of you. If you think that you have an unknown face, I have everybody's mouth shut. So I can figure out who is doing what. You don't believe me that I have everybody's mouth shut? Really? Don't try me. Everybody's mouth shut is here. All right. So, and I update my mouth shut too. Cut off your hair. All right. So I will now get started. Please do not be late, because it really is very, very disruptive when students are late. It's also disrespectful, and that's one thing I can't stand. If students are disrespectful, that really rubs me the wrong way. So I'll start my lecture now, and as you will see, this is the reason why I was asking you guys not to sit at the back, but some of you are pretty obstinate, so go figure it out how it works from there. It's always okay. Generally I write big, but it's not a good idea to set it back to that. All right. So physics as such. Oh, another point I want to mention before I get going deep into this. And this is something actually very important. I forgot to mention it. As I said, the lecture is live. So whatever is going on the board is something that is happening because this is something I want to cover. You may be asking questions. I'm responding to that. That's what goes on the board. The stuff that I cover in the lecture is not covered precisely on a chapter-by-chapter basis in the book. Why is that? The reason is that the purposes are different. The role of the book is to give you the material in a certain order such that if you are self-reading it without the help of somebody with which you can communicate, then it has to be presented in a certain way, right? So the books are presented in a certain way. When I write a paper, I go through the definitions of a whole bunch of stuff before I actually get to the fun stuff. However, when I give a lecture, I don't bore people with the definitions because most of the fun stuff I can get to much more easily because I'm there and I'm essentially addressing any issues that are coming up dynamically. So my lecture, you'll always find, is actually cutting through more than one chapter in a given lecture. So most lectures will involve between 1 and 3 chapters. That's how I pick and choose my material because my job is to cut the best path for you. My job is not to mimic the book. I'm not the book. The book is stuff you use to get through the material. So don't get the impression that you don't need to use the book and it's free and all that. No, this book is as important and as good as any of the good books that are around. Okay? The reason why the book is free is because Bill Gates and Melinda Gates paid a lot of money for it. They are the ones who funded a significant share of the OpenStax project run out of Rice University. And you are a beneficiary of that philanthropic educational effort. But the book is good. It's a very good book. So you use the book the way you should be using it to attend to the homeworks, because I'll be assigning you homeworks from the chapter and problems in the book. But I will be covering material in class that will be cutting through multiple stuff at the same time, because that way I can be more efficient. Otherwise, there is no way on earth I can cover 16 chapters in effectively 12 or 13 weeks. That's just not possible. Okay? Any questions? All right. So, please stop me and ask questions as I go along. Okay? So, in physics, what we are looking after, what we are trying to understand, is a very broad philosophical question: how nature works. So this is really the problem. How does nature work? And that's a pretty serious problem. So how nature works essentially means we are doing a study of nature. And this particular course is focusing on mechanics. Mechanics essentially are the laws associated with motion. Okay, so we are not talking about stuff that's charged and this and that. We are talking about tables, chairs, planetary objects, animals, humans. Don't get the impression that mechanics is very simple and very old-fashioned. Not at all. Some of the most fantastic devices on Earth, or some of the most dangerous phenomena on Earth, arise because of mechanical effects. So we'll come to that. But let me just tell you a little bit about nature. What do I mean by nature when I say how nature works? Well, by nature I mean everything. From the tiniest particles to objects, to an object such as our universe. So you can clearly see that it goes from very small to very, very large, right? So by tiny, how tiny can things be? Well, nobody really knows. But we know for a fact that there is observable nature when you get to 10 to the minus 18 to 10 to the minus 20 meters. So how much is a meter? When I say a meter, what do you think about a meter? Show me by show of hands. How big it is?
100 centimeters.
Huh?
100 centimeters.
Yeah, but
Oh.
pretty big. About 3, a little over 3 feet, right? So 1 meter is about 3 feet. So this basically means 10 to the minus 18 means that's how small it is. So 10 to the minus 18 meters, that's 1 divided by 1 followed by 18 zeros, that is this number. So there is observable, or certainly may not be entirely observable yet, but actually this is observable at that length scale, 10 to the minus 18 meters, even less. Now this is deep inside the atom. Not only that, this is deep inside the nucleus. Okay? So nature can be very complex at the smaller scales, and you may have heard of that there have been dozens of Nobel Prizes given for exploring nature at that level. Now, on the larger end, on the other hand, we go pretty large. So for example, the universe itself, we believe from data, is of the order of 10 to the power 26 positive. So now you have 1 followed by 26 zeros in meters. That's not something for the human brain to comprehend. You can try, that's not a bad thing to do, but it's not something for the human brain to comprehend. So therefore, as you can see, when we talk about nature, we talk about pretty much everything in physics. So nature doesn't mean something that you can easily kind of pinpoint and say, oh, this is what. So anyway, so what about the study of nature that we do? So as far as study of nature is concerned, study is done in some specific ways. For example, for you to be able to study physics, you have to be able to measure something. If you cannot measure it, then you cannot study. So therefore, how you measure enters into the game. Measurement is therefore a very critical part of what has to be done in physics. Now this particular course, of course, is about the laws of physics, and it's a theory course, it's not a lab course. So we ourselves won't be making any physical measurements, but on the other hand, there will be plenty of measurement-related stuff that you'll be doing all the time. So measurement allows you to understand a phenomenon, right? But measurement alone is just measurement. The next part of it is explanation. You explain what you see. And in a course like this, or in any physics course, the bulk of the material that we learn is about how to explain what we see. And ultimately, since this is not about just understanding and explaining, we would certainly like to go to the Mars and the Moon and wherever else. So it is important for us to be able to predict. In other words, our understanding of natural laws should be good enough, should be accurate enough, that we should be able to predict what's going to happen. Now, from measurement to prediction, this chain of events that happens, inside this, there sits two things. One is ideally theory, and not so ideally phenomenology. I'm telling you this because I'm laying the groundwork for how I'm going to start the material in the next few minutes. So, theory and phenomenology is a part of this explanation process. You understand the measurement, you tie the measurement to some meaningful picture that you think is possibly correct. And if you have the theory or the phenomenology, then presumably one would think that you can predict what's going to happen. And that allows you to build new materials, to predict events, whether an asteroid is going to hit us tomorrow. All these things you can find out. How amazing is that? Now, can you predict it with great accuracy? Sometimes yes and sometimes no. But imagine that you can basically do a calculation on a computer or on a piece of paper or some combination thereof and figure out, perhaps, that so-and-so comet or asteroid or whatever can hit us at so-and-so time. That's pretty amazing because it would mean the survival of the human civilization itself. In fact, it might mean the survival of Earth itself. So it is very important, therefore, that we understand theoretically, or at least phenomenologically, what we see. Now, what is the difference between theory and phenomenology? You will not feel this difference too much in the post-light mechanics or even the second semester. But when we say theory, ideally this means that we actually understand a great deal about the processes that we are trying to describe. So typically theory has a higher burden, if you will, in terms of standards as to how well we understand something. Phenomenology is a step before. So in reality, when you see something or when you observe something which is complicated, and almost everything is very complicated, you will go through a series of processes to understand. The first step of that will be phenomenology, where you roughly understand what the phenomena are, what might be the underlying reasons for this phenomena, how things, the aspects of this phenomena can be related. So this is phenomenology. There are many, many areas of physics, of chemistry, of biology, and many, many fields where, for example, the phenomenology itself is very difficult. So just to give you an example, I have a friend in oral biology at UB. His name is Richard Salke, and he's a word expert in hearing. So Richard is 71 years old, and Richard is world famous, as I said, scientist in hearing. But the reason why Richard and I chat a lot and hang out when we can is because I would like to understand what are the phenomena that happens between the ear and the various parts of the brain that allows us to hear the way we do, or not hear the way we should. And it turns out that it's something as old as time almost, as old as human beings have existed, we actually don't even have much of a phenomenology of the process of hearing, let alone the theory. Even the phenomenology is problematic. And so when somebody tells you that, when you use your earbuds, headphones, or whatever, this does no harm, you should take it with a grain of salt, because we don't really understand the process of hearing beyond the point. And what damage happens when when we stress our ears is not something that is scientifically at this point clearly understood. We know a lot about it, but that doesn't mean we understand it. So phenomenology, therefore, is very important, and you will see us do phenomenology, and you'll also see us do theory, although I may not necessarily distinguish them all the time as we go along. Now let me move on to something a little bit more concrete now. Let's come down to earth a little. So measurement. So all measurements involve units, typically. So suppose I want to measure, let's say, the length and the width of this table. So I can express it in some units. I can say, some number in centimeters, or some number in inches, some number in feet, or some number in meters, and so on. So I'm talking length, right? And when I'm talking length, physicists use the following notation. L in square brackets to denote length. This is not necessarily length denoted in meters or centimeters and so on. It's just to say that the width of this table has the dimension of length. Okay? So we call this dimension of length. Suppose I want to find out whether all the gluttony I did yesterday actually added to my weight. Precisely, it doesn't add to my weight. What does it add to? Mass. Weight is mass times gravity, as it turns out. Earth didn't change between yesterday and today. I just ate a whole bunch of steak, let's say. My mass increased. So mass is therefore a dimension. And I can say my mass is so and so kilograms, or pounds, or whatever. So the dimension of mass is therefore denoted by M. The reason why I'm telling you this is because I want to show you a very nice trick by which you can make sure that when you write an equation, you don't make an unnecessary mistake. So I'll show you how to do dimensional analysis, and I will expect that every time you write an equation, you will run a check in your head and make sure that it's dimensionally correct, because that's one way in which you can spot your errors. And by the way, the only way you're going to do well in this course is by knowing your own mistakes and not making them. So my whole emphasis is on teaching my students how to catch their own mistakes before I catch them. So mass and length. What's the time now? The time is, let's say, 10:20. So that has the dimension of time. Time may be measured, for example, in seconds. It turns out, believe it or not, that everything in the universe, and I mean the universe, all 10 to 26 meters of it, that's just the length, not the volume of space involved, can be described in terms of these three dimensions: mass, length, and time. So therefore, there are three fundamental dimensions that we live with in nature: mass, length, and time. So therefore, every quantity that you describe, everything that you write, can be expressed in terms of mass, length, and time. Now, obviously for measurement, we need units. So let us say that we will use the SI, System International, system of units, SI units, or the old name for it used to be the meter kilogram second system. So therefore, the length here is in meters. The mass is in kilograms. And time is in seconds. The other system that's also used is the centimeter gram second system. That's an old system in which length is measured in centimeters, mass is measured in grams, and time is again measured in seconds typically. So now, second may be an inappropriate unit for some measurement. For example, you may be interested in, let's say, how many time taken for an electron, let's say roughly, to move around in an atom. Now, if you're trying to measure that in seconds, you will be dealing with too many zeros for it to be convenient. The relevant time scale for it may be 10 per second. 10 per second would be 10 to the power minus 15 seconds. So therefore, we have all these other units that we use that are tied to seconds. Similarly, we might be using milligrams or nanograms or picograms. So therefore, this is just to tell you that in SI units, the way to express the units would be meter kilogram second. And this is the unit system we'll be using the most. That said, I expect you to know the conversions. That's too elementary for this course. So for example, you should know that 1 meter is equal to 100 centimeter and equal to 1,000 millimeter. So 10 millimeters is 1 centimeter and so on. These are things you should know. Of course, there are tables, and you can look at the tables in the book. But these are relatively simple things that I expect my students to know. So if you are not on top of that, I would encourage you to quickly get on top of it. So let's talk a little bit about derived units. We are talking about the measurement piece, right? So what do we mean by derived units? Derived units, as I said, are units that are sort of tailored for what it is that we are dealing with. So for example, you have something moving, let's say, at 5 meters. So m is for meters per hour. Now that can be a turtle, for example. So 5 meters per hour obviously is not a level of speed, right? That's like 50 feet or so in 1 hour. So meters per hour can be a derived unit. Or if we are trying to write it in another way, we can, let's say the turtle moves 5 meters in however many seconds. So how many seconds in 1 hour? Be brave.
3,600.
Yes, 60 times 60, right? Because there are 60 seconds to a minute, and then 60 minutes to 1 hour. So 60 times 60, 6 times 60 is 36. We are talking 3,600 seconds. So 5 meters in 3,600 seconds. So if you actually do the divisions, and these you will be doing on your own, I will not help you by giving you calculators. This is 0.0014. I'm not doing significant figures yet. Meters per second in the fundamental units, meaning that is NKS units. As you can see, it's very inconvenient because since I have chosen a very large unit of meter, I have to put in so many zeros in the front. So it is better, for example, to write 1.4 millimeters per second. And you can do the conversion because 1,000 millimeters is going to be 1 meter. So it's going to be 1.4 millimeter per second. So these are derived units. So this is a derived unit, that's a derived unit. But this is basically your SI units meters per second. But the point is that SI units may not be the best way to express all the numbers or all the quantities that you may be dealing with. Let us do a conversion, because conversions will probably trip you guys up quite badly for a while. And I'm going to give you some conversion work very soon, in fact today. in terms of the homework, which will be due on Saturday. So let us say you are driving a car at 60 miles an hour. So the speed is 60 miles. I'm not writing meters because I'm using N for meters. So I'm spelling out miles, 60 miles per hour. So I want to convert 60 miles per hour to meters per second. Okay? I want to convert that. Now, one of the things that you will often do in this class is conversions. And you really have to be on top of these conversions. You have to know them pretty cool. So, some things you need to know. And if you get stuck, you can ask us, I'll tell you. So 1 mile is roughly 1.6, or more precisely 1.609 kilometers. So a mile is a larger unit than a kilometer. So therefore 60 miles, which is the numerator here, 60 miles divided by 1 hour. So 60 miles should be written like this if you want to convert it to meters per second. So the way you want to do it is you want to write 60 miles. Don't be lazy and not write the units, okay? That would be the kiss of death. Times 1 point, let's say 1,000, okay, I won't put a comma, 1,609 meters, because 1.609 kilometers, if you multiply by 1,000, is 1,609 meters. And this is 1,609 meters to a mile. This is the way to write it. As you can see, the way I have written it is 60 miles, which is this 60, multiplied by 1,609 meters to a mile. That's how this piece is to be interpreted. So let me put it up here. Oops. So therefore, I have converted 60 miles to 60 times 1,609. And this number now is going to be the number in meters. Okay? The miles and the meters per mile, the miles cancel out over there. So now I have to convert 1 hour, and we already saw 1 hour is 3,600 seconds. That was easy. The way I would write it though is I would write, following the same principle that I'm trying to ask you to follow, just so that you don't make unnecessary mistakes, is 1 hour to 3,600 seconds per hour, or 3,600 seconds to an hour. So that way you can see, you can make sure things are right, because the hour should go away. You are converting to seconds, the hour should go away. One is in the numerator, one is in the denominator, and therefore you are left with 3,600 seconds. So therefore 60 miles an hour, quite simply, is 60 times 1,609 in this case, and then denominator would be 3,600. So this part would be seconds, and this part would be in meters, ultimately. So therefore, if I do the multiplication, it will come out to a fairly complicated number. But because you are not using calculators, I will often do this in class as well, and I expect you to do the same way. I'm going to approximate that. So that will be like 60, let's say, instead of 1609, I would write 1600, simplify that. Now I have 3600. I already know that 60 times 60 is 3600. I can get rid of a 0 dividing by 10 both ways. So I'm left, therefore, with 160 by 6, which is same as 80 by 3. And this is approximately 27 meters per second. So this is the kind of approximation I would expect you to do. And as you can see, it's not difficult, but it does require some introspection and some practice. Any questions so far? No questions. Sure? All right. Keep going. So similarly, you can do other conversions also, but let me not belabor this point. I've already shown you a few conversions. Let me now get into the business of talking about explanations and predictions. This is the part that I haven't talked about yet, right? So how do you do these explanations and predictions of what's going to happen or of observed phenomena? The way you do it is by using equations. So equations obviously involve physical quantities, and therefore to be able to write an equation, you need to make some observations, measurements and so on, from which you make an inference as to how to describe something. Suppose that you are in the space station. This is a cartoon of our space station, let's say. And since we are doing only cartoons, I'll make a cartoon of you. That's you. So you're in the space station. And in the space station, what is special? Right? No? No. No gravity. So if there is no gravity, will you be able to walk? No. Tough luck on that. So what will you do? You will be able to drift, right? So suppose this is how you look in the space station because you cannot walk. Then g is basically 0. And suppose that somebody has the good idea of pushing you gently. And then you are probably going, let's say, for argument's sake, from this end to that end. And you're moving, let's say, at some speed v. So when you find out, you're wearing a watch, the watch works, and you find out that you have moved for a few seconds. So let's say the time to which you have moved is time t. So what does Vt give you? Distance. Why does it give you distance? How do you know it will give you distance? So let's call it d, big D. So this is an equation, right? Distance d is v times t. Now to make sure that I haven't screwed up, because everything in physics is about not screwing up. If you screw up, bad things come out. You can't predict. So distance is measured in what? Length. L, right? So if I want to write it dimensionally, the left side would be L, right? I'm doing what is called dimensional analysis. So I'm doing dimensional analysis. So every time you write an equation, what I want you to do, just so that you don't make unnecessary mistakes, is to be able to smart enough to catch your own mistake. Why do you want to shoot yourself in the foot? So therefore distance is going to be length. What is the dimension of t? Obviously time. Now, can the left side and right side have different ultimate dimensions? No. Because that would be like apples and oranges, or worse. So therefore, v, the speed at which you are moving, must be such that eventually in the right-hand side you come up with length. So therefore, this has got to have the dimension of L divided by t, because in that case, these two guys will go away, and you'll be left with length and length on both sides. And then you're talking that the equation is dimensionally correct. On both sides, you have the same dimension. So dimensional analysis of an equation, therefore, necessarily means that the left side of the equation and the right side of the equation will have the same dimension. Cannot screw that up. If you have made a mistake here, that means you have written something incorrectly in the equation. That's the reason why this is a way in which you catch your errors. And mind you, when you write an equation, 70% of the time you will make a mistake. That's what happens to everyone, including me. The difference between a student and a professional is that I have become better at catching my mistakes. And that's why I'm telling you that to become better at catching your mistakes, rule number 1, don't screw this up. So I'll actually hold your feet to the fire on this. If I ever find you making dimensional mistakes in quizzes or in exams, you better watch out. Because I'll catch you on that and I'll tell you that that learning stuff will error. Alright. Now, like any old equation, I can think of d equal to vt in the standard form in which equations show up. Equations typically, equation for a line is written as a line, okay, so is in this form, where this is the x-axis, this is the y-axis, and this is, let's say, a line, and this is b, and the slope of this line is m. Okay. What is slope? I'll tell you in a moment. But this is a line after all, and this is the equation for a line. So by slope, I typically mean, for example, if I take any 2 points here, then this is, let's say, some value x2, this is, let's say, some value x1, and this is, let's say, some value y2, and this is some lower value y1. Then by definition, the slope m is y2, which is larger value, minus y1. In this case, not larger, but later. So y2 minus y1 divided by x2 minus x1. So do not mix up the order. So you cannot write y1 minus y2 divided by x2 minus x1. Okay? Then you will get the wrong result. So this is the slope, y equal to mx plus b. And this intercept, this is called the intercept. This intercept is b. So if you look at that equation, and if you look at that equation, what does this one look like? Can it be written in terms of an equation for a line? Let's take a whole. Whole things that cannot be written in terms of an equation for a line. Come on, you don't have a choice of not voting. That is illegal. Tell me if d equal to vt, whether that is similar or not to y equal to mx plus b. I'm ready. Yes. It is similar. So one person has voted. What about the rest of the people who are dozing off here and there? Tell me.
So the slope is b.
Big?
Not the slope. This is b.
No, b is the intercept. There. But here in b equal to vt, is this an equation for a line with you?
I mean the m is equal to b. Right? It's the same thing.
Okay. Yes.
It is similar or related because x, if we were to graph it on a plotted line, x would be time and
Right.
y would be the velocity.
Y would be d, and x would be t. Okay, good. So you guys are coming along. So what I'm driving at is if I plot time here, and if I plot the distance traveled by you with the space station here, then at time t equal to 0, the way I have set it up, distance traveled is 0. So this is basically a line. Okay? So I can picture the idea that I'm trying to give you is that I can picture this equation in terms of a graph like this, where the slope of this line is v. Okay? So you might think that this is very simple, but this is just one way to picture. That's not the only way. So anytime you write an equation, you are getting to a point of maturity now that you need to think of this equation in terms of a graphical picture. Because why? That gives you analytic power, or power to dig deeper into what is being said and make inferences that you otherwise cannot make if you don't do that. So that's something I'm again going to insist that we learn to do now. So d equal to vt therefore can be thought of as t along x-axis, t along y-axis, and this is going to be the slope. The change in d for the corresponding change in t. Now, can time go along the y-axis? Over there, I have made time along the x-axis. Is there a problem if I put time along the y-axis? No. Would you do that? Easily? You would do that.
But like it's time
time isn't dependent?
Yes. So time is an independent variable, right? You cannot control how time is going to flow. So usually, by convention, we put the independent variable, in this case that is time, on the x-axis. And we put the dependent variable, which should be y, along the y-axis. So that's a custom that we follow. As she said, there is nothing sacrosanct about this custom, but this is custom all across the science, not physics alone. So independent variable, so you need to know that which one is the independent variable and figure out which one would be the dependent variable. In many problems, this is a critical part of the analysis of the equation that you are trying to do. All right. So clearly then we have covered this equation. The last thing I want to say is that, as I said, that d equal to dt can be pictured this way, but this is by far not the only way. Suppose instead I decide to plot time along the x-axis and velocity, or the speed, along the y-axis. There's nothing wrong in that. In fact, if you look at this equation, let's say your speed was fixed from time t equal to 0 to some time t equal to 1. Then the velocity was this, the speed was this, and basically you will have a plot like this. Now this is a plot of a rectangle. What does the area of this rectangle tell you? How do you measure the area of a rectangle? Length times width. So here you can say that the length is time and the width is velocity or speed, right? So Vt is the area of a rectangle. So what physically is the area of the rectangle telling you? Distance, right? So pictorially then you can figure this, you can describe distance in this case, which is a length, as an area, but in a velocity time plot. These are the ways in which I want you to understand the equation. Now you can say, why do I care? Well, the reason you care is because suppose the velocity is not fixed. I can still get away with the same picture and define an average velocity or average speed. And once again, after describing an average speed, I can just measure the area and give you this. If you want to do it some other way, it's much harder. So this is a concept that we'll be using very soon, actually. Not today, because we are dead out of time. But on Thursday, we will build from this and introduce gravity, which we have turned off in the space station. Thank you.